All right, welcome back, guys. So this is our last topic here in Unit 4. It's called L'Hopital's rule. This is named after a French mathematician, L'Hopital. And we're going to use this to evaluate indeterminate limits, which we had talked about back in Unit 1. So quick little review. So we saw indeterminate limits anytime you got 0 over 0 for your expression. So you have limit as x approaches -1. You see you get 0 over 0 there. This is based off, you factor this, x squared minus 1. And then that becomes x minus 1, x plus 1. X plus 1's cancel, leaving just 2 times x minus 1. And now we can fill in, and we get -4 ultimately for that one. When limit as x approaches infinity, technically this would create an infinity over infinity, still indeterminate, but we recognize this was based off the rule of dividing each thing by the highest power of x. So we're dividing every single term by x squared. So you'd get this right here. And as you're going to infinity, the fractions go to 0. So you're left with just simply 3/2. And that was great. But we purposely only talked about these things for polynomial functions that could factor, limits at infinity with polynomial functions or square roots. We talked about e's with infinity, but we never really went into what's indeterminate for an exponential or for a trig function. And that's what we have right here. Because if you substitute 0 in for x, you have 2 times 0 minus 1 there. That becomes e to the 0, which is 1. 1 minus 1 is 0. And we get indeterminates. And there's no factoring of e to the 2x minus 1. This isn't approaching infinity, so it's also not polynomial, so we can't divide by the highest power of x. So we were kind of stuck. And there are ways to handle this. Different rules behind the exponential, different rules behind different trig indeterminate forms, but I had purposely, for our class at least, did not talk about that because of this rule right here. Because this rule right here allows us to avoid memorizing a whole bunch of, in my opinion, unnecessary limit rules. Because all we really have to do is, so again, that's just review right here, getting 0 over 0, infinity over infinity, those are all indeterminates. L'Hopital's rule, though, we just take the derivative of top and bottom. Now, couple things about this. This is not a quotient rule. So even though it's based off a fraction, you are not doing the quotient rule. You're doing the top function its own separate derivative, bottom function its own separate derivative. This rule also only works if the function is indeterminate. So if it's not indeterminate, this will not work. So like if, for example, I have the limit as x approaches 3 of x squared minus 9 over x plus 4. If you were to substitute into this, we'd have 3 squared minus 9 over 3 plus 4. We'd get 0 over 7, which is supposed to be 0. If you tried applying L'Hopital's rule, taking the derivative would give you 2x over 1. So it'd be 2 times 3, which is 6. Those are not the same thing. Okay? So this rule only applies if it's indeterminate. So like all other limit questions, you must always substitute the value of x or whatever we're approaching, this variable approaching this number, in first, confirm its indeterminates, and then apply L'Hopital's rule. So all those things we did in Unit 1, the different factor rules, the rationalization, the complex fractions, every one of those could also be solved with L'Hopital's rule, though in most of those cases, especially the factoring ones, I would find it easier just to factor and cancel rather than going through this derivative process. Also, especially really with the radicals, because derivatives with radicals can be a bit messy. All right, so we're going to do a couple examples using this. So first thing we do is we're substituting into this. So we have 2 minus 2 up top, 3 times 2 cubed minus 6 times 2 squared plus 2 minus 2. We get a 0 up top. The 2 minus 2 will cancel each other. 2 cubed is 8 times 3 is 24. 2 squared is 4 times 6 is 24. We again get 0 over 0, so it's good to go. So we go ahead and immediately take the derivative of numerator and denominator. So we have the limit as x approaches 2. The numerator is now a 1. Guaranteed now not to be indeterminate anymore because there's no more way to get a 0 up top. Denominator would be a 9x squared minus 12x plus 1. We now fill in the 2, so we have 1 over 9 times 2 squared minus 12 times 2 plus 1. And we're going to ultimately get a 1/13 for that answer. All right. So it's a very straightforward process as long as you're comfortable with your derivatives. This rule works out very easily. but always substitute in first, verify it's indeterminate. So the trig one right here, this sine, there's a way to use, there's a special trig rule involving sine and cosine. The sine rule was limit as x approaches 0 of sine x over x is always going to equal 1. And this is kind of where that's coming from using your L'Hopital's rule. So we go ahead and just set that up first. Sine of 6 times 0 over 0. We get sine of 0 over 0, which is again 0 over 0. So we apply L'Hopital's rule. We take our derivative. Derivative of sine becomes cosine. Derivative of the angle is 6, so it's 6 cosine 6x. Derivative of x is just simply 1. So we substitute into 0 now. We get 6 cosine of 0, and cosine of 0 is 1, so we just get an answer of 6. All right. And again, there are ways to manipulate the sine 6x over x to create the rule right here, which is what some teachers will have you do. Again, I purposely avoid it because L'Hopital's rule, this is a much quicker, elegant process, less you have to have memorized. Cosine is another rule that we could work with for that. There was a rule involving your cosines. The rule was limit as x approaches 0 of 1 minus cosine over x. That was always going to be 0. So kind of manipulating that, we can kind of get that same kind of thing here, but we're just going to go ahead, substitute in, recognizing we have 1 minus cosine of 0 over 0 squared, 1 minus 1 over 0, 0 over 0, again, indeterminate. So we apply L'Hopital's rule. We get a positive sine x over 2x, and we substitute in. So we have sine of 0 over 2 times 0, which is still 0 over 0. And here's the beauty of L'Hopital's rule. It's still indeterminate. We just apply it a second time. We keep on applying L'Hopital's rule to each new function, keep on taking a derivative top and bottom separately until we no longer have an indeterminate result. Eventually it will go away. Typically, you only really have to do it at most twice. You might have to go a little bit further sometimes. So sine x becomes a positive cosine x. It's over 2. So again, we plug in cosine of 0 over 2 is 1/2. All right, so again, it's entirely possible we do this more than once. That's okay if we have to. Just keep on going through each new iteration of the L'Hopital's rule. Let's just do one more. Let's do one involving e involving x to infinity. So here you can see you've got 2 times infinity squared over e to the 2 times infinity. You're going to get infinity over infinity. So that's obviously indeterminate. So we have to go through and apply L'Hopital's rule. So limit as x approaches infinity. We'll get a 4x over 2 e to the 2x. This is still going to be infinity over infinity, because you can see 4 times infinity over 2 e to the 2 times infinity. We still get infinity over infinity. So still indeterminate. So we do L'Hopital's rule one more time. Limit as x approaches infinity. We now get a 4 up top, a 4e to the 2x on the bottom. So we can also cancel those 4s. We're like 1 over e to the 2x. So guaranteed not to be infinity over infinity or 0 over 0. Now we substitute in, so it's e to the 2 times infinity. We get 1 over infinity, and 1 divided by infinity is always 0, whether it's positive or negative infinity. All right, so doesn't matter what x is approaching. Nice integer, fraction, 0, infinities, weird numbers, whatever it is. Just substitute into it, verify it's indeterminate, and then just take derivative of 2 separate parts. None of these were quotient rules, so we're not going through that process, just 2 separate function derivatives. All right, so that's it for Unit 4. That's our first unit in the applications of the derivatives. Next up, Unit 5, we'll be talking about applications more along the lines of creating graphs and how we can interpret that kind of information. So I'll see everyone next time for Unit 5.